I hope everyone had an opportunity to look at the review that I sent out. Anybody need a copy? I've got them right here. Anyone else? So on this review, just to explain where it came from, the typed side of the page, 21 problems or so, is actually the review that Ms. Schmidt, Christy Schmidt, had originally planned for you to have. So this is the review from her, and then on the back I added another 7 questions that some of them are similar to some things on the front side, but you know, just a couple of additional things to practice. So I was really hoping that this would be something you would go through and work out and then come to class with questions. I did work out all the solutions. Did those go out? Did you see those? Yes. I did work out all the answers for the first 21 problems, but I kind of ran out of time and I didn't have time to do the back. So that's what I'm gonna pick up with today, unless there are specific questions. But today we are going to start Chapter 9. We're going to cover the law of sines. Now this is not going to be on your test, all right? And I realize right before a test, the last thing you want to do is have new information, but we still have to continue moving on, and we only have 2 more days after today. I mean, well, we'll have a test, but then after that, 2 more classes. So I need to get through law of sines and cosines at the minimum, so I'm going to do that today. After we finish law of sines, I will start entertaining questions on the review, all right? And then, of course, on Wednesday is our test, unless you said you're going to come in and do it next week. Okay, so the law of sines it's basically a formula. It is not on your formula sheet. All right, it's not on here. And what I'll do is I'll allow you to write it on the back of the sheet. All right, law of sines. But let me tell you where it comes from. Let me show you where it comes from. The first thing that we do is we label a triangle as I've shown here. So the triangle has 3 sides, right, and 3 angles. We label the angles capital A, capital B, capital C. We label the sides little a, little b, little c. And notice how we're labeling these. Angle capital A, right, corresponds to little a, which is the side opposite of that angle. Capital B, that angle, you look at the side opposite of that, that's little b. And then capital C, you look at the side opposite of that, and it's little c, all right? If we agree on that convention, as far as that's the way we're going to label triangles from now on, then we're going to be able to develop the law of sines. Now, also notice this is not a right triangle, okay? If this were a right triangle, we would have a relationship between the sides, wouldn't we? A squared plus b squared is c squared if it was a right triangle, but it's not. So the law of sines is a formula we use when we do not have right triangles, all right? That's what makes it so special. So let me develop what the law of sines is. Actually, you know what? Let me write it down first, and then I'll show you where it comes from. How about that? All right? So here's what law of sines says. It says that if you take sine of angle A and divide it by little a, so if you take sine of the angle A and you divide it by the side that corresponds to that angle, that should be the same as sine of angle B divided by little b. That's like a formula, isn't it? Right? That's a formula. It relates 2 angles to 2 sides. But this formula can also be extended to the third angle, which is sine C must be, sine C over C must also be equal to that. So this is saying that the ratio of sine of the angle over the corresponding side should be the same for all the angles in their corresponding sides. Now, I'll show you where that formula comes from in a second, but I also want to point out that we can also write this a different way. We can write it A divided by sine A must be equal to B divided by sine B must be equal to C divided by sine C. So in other words, you can flip all the fractions over and you have the same string of equalities. Now, which one of these you're going to use, right, if you're going to use the top one or the bottom one, would depend on the problem and what you're trying to figure out, right? But just keep in mind that you can flip them over. Now, let's talk about where it comes from. So you see my picture here, right? What I'm going to do is I'm going to, right here at angle B, I'm going to drop what we call a perpendicular. I'm going to drop a perpendicular line down right there. Now that means from that corner, I drop a line straight down so that it hits this side at a right angle. Y'all all right with that? I'm going to label this side, I'm going to call it H, because normally that would represent the height of our triangle, wouldn't it? Okay, now let's set up some relationships here. What is sine of A? According to this triangle, what's sine of A? Sine of A, the definition of sine on a right triangle, right? If I have a right triangle right here, what is sine of A? Sine is opposite over hypotenuse, correct? Which would be what? Height over C? Everyone agree with that? It would be the height, which is the opposite side of the right triangle, divided by the hypotenuse, which would be C. Do you all understand that? Okay, now I want you to look at a different triangle. Let's look at this right triangle over here. What is sine of C? Sine of capital C is, what is it, H over A? Again, because the opposite side would be H, and then the hypotenuse would be A. Is that all right? Now, for each of these equations, I would like for you to get H by itself. So on this first equation, multiply both sides of the equation by C. If I multiply this side by C, I get C times sine A. If I multiply this side by C, the C's cancel, and I just get H, don't I? So this gives me an equation that says C times sine A must be H. Do the same thing on this one. So I'd multiply both sides of this equation by what? A. If I do that, A over here, they cancel, and I get a new equation, A times sine C must equal H. Is that all right? Now, if this must be H, and this must be H, right? If they both have to be H, I can set them equal to each other. So set each of these equal to each other. So the result of this is that C times sine A must be equal to A times sine C. And do you see what I can do now? What I'm trying to show you is this first, well actually it's going to be this one and this one, that these two are equal. I'm going to show you that these two are true. So what I can do here is divide both sides by A, right? If I divide both sides by A, the A's cancel. And then simultaneously divide both sides by what? C. The C's cancel here. So what you're left with is sine A over little a must be sine C over little c. And that's our first little equation for law of sines, the ones I circled up there. Do y'all see that? So how would I prove to you that this middle one is true? What I would do is I would have to start over by redrawing a new triangle. All right? I'm not going to do it. But I would, instead of dropping a perpendicular down from angle B straight down, I would drop it from angle A. It's kind of a bad picture, but I would drop it from angle A down. And then I'd have two different right triangles, and I would do the same thing, and I would show the same relationships. Is that enough to convince you? I mean, that's all I'm trying to do is just show you it comes from somewhere. It's not just like, you know, arbitrary, just someone just created it, made it up out of nowhere. Okay, so using that, let's see how we can apply that to something. Let's say that we have the following example. So this was note, let's call that 921. Let's say I have a triangle that looks like this. So I tell you, this side is 60 degrees. This side is 40 degrees. Or side, sorry. That angle is 60, that angle is 40, and then this side is 4. And I ask you to solve the triangle. Well, first we have to understand what we mean by solve the triangle. Solve the triangle means give me all the angles of the triangle and give me all of the sides of the triangle. So you should have 6 total things, right? 3 angles, 3 sides. If you have all those, you have solved the triangle. All right, is there anything that you can see here that you can get without doing a whole lot of work in terms of angles? You can get the third angle, can't you? Now, why can you get the third angle? Because you know that when you add up all the angles of a triangle, what does it have to be? 180? Are we all comfortable with that? The sum of the angles of a triangle is 180 degrees. So what I know is this. Let me label some stuff here. I'm going to call this angle here A, which means this side opposite of it is little a, right? Call it something like that. This is A. Capital A is the angle. Little a is the side. I also need to know what this side is, so why don't I label this side little b? Is that all right? Can you tell me what these 3 angles are? Well, angle A we don't know, right? Angle A I have no idea. What's angle B? Yeah, it's the one that corresponds to this angle across from it, so 60 degrees. What's angle C? 40. Well, I didn't label it as C, did I? But if I did it this way, then 4 right here would be my C, wouldn't it? Little c, capital C. So let's see what we have over here. Little a, little b, little c. Which of these do we know? Just little c, right? Little c is 4. And we don't know this, and we don't know this. Okay, so that's just me listing out all the information and labeling my triangle ABC so I can get everything in order. Now we said about angle A, what did we say? Angle A, how are we going to get this? Well, I know that angle A plus angle B plus angle C must be 180 degrees. On all triangles, that's true. And so I have A plus 60 plus 40 must be 180, which means A plus 100 degrees must be 180, which means A is 80 degrees by subtracting 100 on both sides, right? Now, you could have done that mentally. You don't need to necessarily write it down, but I'm just, that's the systematic approach to it. Okay, so we have now 3 of the angles. We need to get to the other 2 sides, right? So let's start with side little a. Let's start with that. And let me go up to the law of sines and take a look at where in my law of sines, which is, I'll box right here, this is my law of sines. I'm going to solve for little a, right? So what I'd like to do is use one of these equations that has little a in it, but on the top, because that's what I'm solving for, right? Here, little a is on the bottom. I don't want to use that because then eventually I'd have to get it out of the bottom. So why don't I use this one right here, the one that's a over sine a, all right? And now what I can do is I can set that equal to either b over sine b or c over sine c. So let me write down. Using law of sines, I have A over sine A must equal, now what are you going to use here? Can you use B over sine B? No, because you don't know what B is, right? You don't know what little b is, so you can't use that. Do you know what little c is? Do you know what big C is? Yes. So let's set it equal to C over sine C. So I'm going to use that. This ratio is the one I want to make true. Now let's just replace everything we know, right? We know what capital A is, we know what little c is, we know what capital C is. So this equation turns into A over sine of what? What's capital A? 80 degrees equals C, which was given to us in the problem is 4. And then capital C here, so sine of 40 degrees. That makes sense? Now, 80 degrees, right, that's an angle. We can take sine of 80 degrees, but it'll require us using our calculator. Sine of 40 degrees, it'll require the calculator, right? Those are not common angles. And so at this point, we're going to break our calculator out for most of the problems we do today. So watch what I do here. I'm going to get A by itself, little a. I'm going to multiply both sides by sine 80. They cancel on the left, and that gives me a nice equation for A. A equals 4 times sine 80 over sine 40. You get the idea here? So now, on my calculator, I'm going to make sure that I'm in degree mode because my angles are given to me in degrees. I don't know what mode I'm in. Oh, I was in radians, so that would have been a problem. So I'll take this kind of slow. Sine of 80 degrees. So if I take 4 times sine 80 on top, I get 3.93923, something like that, 1. That's what I get on top, over sine of 40 degrees, which I get 0.6427876. If I divide those two, I'm going to get something close to approximately 6.128. Anyone getting something close to that? Yes? So now I know what A is. All right? I've got A. So coming back up here, 6.128. Up here, this is 6.128. And now I need to know what little b is, right? Now, can I use a squared plus b squared is c squared to get b? No, because it's not a right triangle. So unfortunately, you have to go and use law of sines again. So this time I'm going to be using the formula that has b in it and b on top, right, to solve for b. And then I'm going to set up a ratio just like I did here. So let's do that. I'll have to go to the next page. So I'm going to be using this one. B over sine b must be equal to, now what should I use here? A over sine A, C over sine C. C over sine C. Now could you use A over sine A? Do you know what little a is? Now you do, right? You didn't before. So you could use A over sine A right now. But since you solved for little a, what if you made a mistake? Then that little a is going to throw off this answer too, isn't it? So I would always stick with the ones that you know are for sure, the ones given in the problem. So I would just set this ratio up again. 4 over, well, let me put C over sine C. So here's what we get. B over sine of B. What was B? 60 degrees. Equals C, which was 4 over sine of, what was 40? Sorry. And now let's multiply both sides by sine 60 to clear it out on the left side. So we're going to do on our calculator 4 sine 60 over sine 40. 5.389, something like that. Approximately 5.389. That's good enough. So I have all my angles, right? I have all the sides. 5.389. Let me go back up here and put it in. 5.389. Nope. 5.389. All right, we have solved the triangle. All right, you see the way that works? You can't do it with Pythagorean because it's not a right triangle, and so the law of sines is the most efficient way to do it. All right. Now, on a little side note, we said that the sum of the angles of a triangle is 180, right? Which is true, but I want you to consider something. Imagine that you live on the surface of a sphere. This is a side note, okay? This is not really related to it's related to the class, but it's not going to be tested. Imagine you live on a sphere, kind of like we do, right? Okay. And imagine you want to draw a triangle on a sphere. Well, a triangle on a sphere should connect 3 points, correct? So let me just pick 3 points, and I'm going to pick them. I'm going to pick the North Pole because most people are, okay with where the North Pole is. I'm going to pick a point on the equator, which is here. I'm going to pick another point on the equator, which is here. I just picked those so that, North Pole and equator, just so it'll make it a little easier. If you draw a line from connecting the 3 points, right, straight lines would cut through the sphere, wouldn't it? Because there's curvature. If I drew a straight line from this point to this point, I would have to go through, let's say, the Earth, right? I would have to go through the Earth to connect those. So on the surface of a sphere, if we live on the sphere, we're not allowed to cut through the sphere, right? If we wanted to measure the distance from the North Pole down to that equator, we'd have to measure it over some arc, right? It would be some arc. So the straight line would look like this. Even though we know it's not a straight line, right? That's what we would appear to be doing. We would travel straight from one point to the next, correct? And then, let's say I did the same thing to the other point, like this. And then I connected the 2 points on the equator together. That's what a triangle on a sphere looks like. It's different than a triangle on a flat sheet of paper. And so imagine that you are looking right here at this point right here, that one in yellow. What would be the angle at which those two lines come together? What would be that angle? You see, it's kind of weird because they're not straight lines. You'll follow me or not? Okay, so imagine you're coming along this blue curve, and when you get here, all right, you'd be almost like straight up and down, like this. And if you're coming along this curve, you're curving, and then you come to a point like this. Those two lines should hit each other at a 90-degree angle. Do y'all buy that? I mean, if you look at not the line, but like what we would call a tangent line almost. The line that would be tangent to the curve would be straight up and down. This one over here would be perpendicular to it, or 90 degrees to it. So it would cross at a T. So this angle right here would be a 90-degree angle. And then what about this one over here? That would also be 90 degrees. Now what's wrong? That's already 180. And we haven't even considered the angle up here, have we? So the reason why I'm stating this is because, look, the way math works is that we have a set of rules for a specific geometry system. Okay, everything that we're studying in this class is called Euclidean geometry, right? Euclidean geometry. You take a triangle on a flat piece of paper, the sum of the angles is 180. Another thing in Euclidean geometry you're used to hearing, two parallel lines don't intersect, right? You've heard that? Two parallel lines don't intersect. That's true in Euclidean geometry. The sum of the angles of a triangle is 180 degrees in Euclidean geometry, in two-dimensional space. However, if you change your geometry system to something different. Like instead of having to live on a flat sheet of paper, now you can only live on a sphere. That's called spherical geometry. Then the sum of the angles of a triangle is not 180. It's something else. So we have a whole different set of rules for that sort of system. Does that kind of make sense? I'm just trying to get you to see that, like, if you ever remember that show, Who Wants to Be a Millionaire, right? Where they sit down and give them these questions. You know, if they say the sum of the angles of a triangle is option A, 180, option B, 270, option 3, whatever. Option 4 is you can't tell unless you know the system of geometry, then that would be the correct choice. It just depends on where you are. Am I making any sense? Okay. I'll give you the other one since I brought up parallel lines. Two parallel lines, as far as we know, never intersect each other, correct? I mean, like if you were to imagine two parallel lines, the whole idea is that they don't hit each other. However, there's a different geometry system where they do hit each other. And anyone who's ever done any art or drawing or perspective drawing, have you ever had to try and draw three-dimensionally? Anyone here taken a drawing or drafting or anything class? Okay. They have this thing that they call, let's see, if I draw, well, let me do it this way. Let's say I'm trying to draw a street. Here's a street. Here's a couple of buildings on the side of the street. I'm looking from the top down. Do y'all see the street with the buildings? That's a pretty crappy picture, right? Someone tells me draw a street with a couple of buildings. There it is. That's like, you know, second grade level. So how do I get a little better? I try and make it look like what we actually see with our eyes, right? Now, I'll point out before I demonstrate this. I want you to notice that the ideas are all good here. All these lines are parallel, aren't they? All those yellow ones, they're all parallel. And they never hit each other, right? Like all the parallel lines never intersect. That's why that's a decent drawing. You know, my street would suck if those two curbs came together, right? So what I do to trick your eyeball is I imagine that those two lines, right, the street, they actually do intersect. Even though we know they're parallel, they do intersect. They intersect way far away at this thing we call the, where am I drawing people? What do we call that point? No? Vanishing point. Call that a vanishing point. And then we bring the street down the center like this. And then we draw our building so that all the edges of the building, what do you notice about all the parallel lines here? Where are all the parallel lines going? All these lines that were supposed to be parallel are all going where? To the same exact point. They actually do intersect. The parallel lines intersect each other at a place we call the vanishing point, right? This is called perspective geometry. It's different than Euclidean geometry. You can't use the laws of Euclidean geometry if you want to draw three-dimensionally. You can't do it. You can't get the effect that you want to trick your eye. So I'm just sharing this with you because I want you to realize that, you know, it's kind of like what I call the fishbowl idea. This is a fish, okay? And is most people who are in a class like this are basically like the fish in the bowl. Okay, I'm not saying, don't take offense to that. All right, it's just the fish. As far as the fish is concerned, the bowl is the entire universe. I mean, that's the world. I mean, the analogy would be, you know, a fish in the ocean. I mean, to the fish, that's it. The ocean's it. There's nothing. There's no land. There's no mountains. There's not a mountain goat up there, right? Has no idea of that. No concept of that. So our geometry system is like this fishbowl. What we need to understand is that everything we do in this class is just in this fishbowl, but mathematics actually goes beyond that. And what we do is we have different systems of geometry that suit the different situations in the real world. How often are we stuck on a flat sheet of paper? Not very often, right? How many times are we on a sphere? All the time. So what we do is we start with basic flat paper geometry, and from that we can extend it to the things that are more applicable to the real world. I hope that makes sense. I'm just trying to open up your perspective a little bit, realize that there's more to this than meets the eye. All right, back to the law of sine. Let's see, let's try something else. In that particular problem, I want to point out in that particular problem, what was it that I gave you? Okay, what was given in the problem? Well, we were given two angles, right? and one side. Right? Two angles and one side is what was given. And the book refers to this. I'm not real big on this, all right, but I'm going to point it out. Side angle angle. Okay? If you want, you can write that down, side angle angle. This is the approach we used when we had side angle angle. What if we have an angle, a side, and a side? That'll be fun. Right? That'd be asked. And it's just an excuse to write it. No. Let's take on that in a second, okay? Yeah, we'll do it now. So here's 9.23. All right, so this time I'm gonna not draw a triangle. I'm gonna give you the information. I'm gonna give you A is equal to 3. I'm gonna give you B is equal to 2. And I'm going to give you A, capital A, is equal to 40 degrees. Most of the times when we deal with these problems with law of sines, almost all the time, it's always going to be in degrees. So I know I said we like to do radians and everything like that, but for some reason when it comes to solving triangles, we like to be in degrees. So I'm given in this problem, what? Two sides in an angle, right? So if you want to go with what the book is going to say, they're going to say, they call this the side angle, because they don't want to write ass, I guess. So if you want to write ass, you can write ass. It doesn't matter. Again, I don't look at it this way because I don't like to say, okay, this is the case where we have it. I just look at what I'm given and go for it with law of sines. Like, what can I do? All right? So let me try and determine what the things are I'm going to need, right? So what am I going to need to find? Well, I want what? I'm going to need capital A, right? Capital B, and little a, right? Those are the things I'm going to need to find. What's different about this problem, right, compared to the last one, is that we had two angles so we could get the third, couldn't we? Here we don't have two angles, so I can't tell you what those two other angles are. So what do we want to go after first? Well, wait, why did I put little a there? What did I mean? Little c, sorry. I want capital A. Oh, what the hell? I tell you, this is why I don't teach 9 a.m. classes. It's just I can't get it together this early. This is what I want. Capital B because I don't have capital B. I want capital C because I don't have capital C. And I want little c because I don't have little c, right? Any ideas? So you want to go after capital B? Yes? Okay, what are you going to use to get capital B? The information you have on A, right? Because you know what capital A is, you know what little a is, don't you? That's a good thing. All you would need then is to find to get capital B. All you would need is to know little b, which you have. So I'm going to set up this ratio. Now, which way do you want me to set it up? If I'm going after capital B, sign B on top. Instead of doing the little b on top, sign B on the bottom, I'm going to write it this way. Sign capital B over little b must be equal to sign capital A over little a. And again, the reason I'm doing this is because everything I have highlighted there is something I know, right? I know what all of those are. So let's fill it in. Sine B over little b, which is 2, must be sine of A, which is 40 degrees, over little a, which is 3. Now to get sine B, what am I going to do? Multiply both sides by 2. So I get sine B is, let's see, I'm going to write it this way, 2 sine 40 over 3. So the 2 just goes on top with the sine 40, and then I still have division by 3, and I get on my calculator and I figure out what that is. I'm getting something like 0.42852, something like that. So I know that sine B must be 0.4285, I'll say 3. And that's approximately, right? Approximately equal to that. I'm rounding a little bit. Now, does that tell me what B is, capital B? No, it tells me what sine of capital B is, right? That's not what I want. I want capital B. So how can you release capital B from sine? Take the inverse sine on both sides. That's what I'm going to do now. But as soon as I introduce the inverse sine, what am I doing? I'm restricting my domain. Remember that? That's very important. It's going to come up, not on this problem, but later on it will come up. We won't see those today because we're going to start reviewing here pretty soon. But next time we meet, when we pick up with this, you'll see that it's very important that we take into consideration the restrictions on the sine. So sine of B is this. I take inverse sine on both sides, or arc sine, right? That's the other name for that. I get on my calculator. I figure out what arc sine of 0.42853 is. I'm in degree mode, so my answer is going to come back to me in degrees. I get that B is approximately equal to 25.3743. Degrees, sorry, degrees. B is an angle. Okay, now here's where I had to be careful. Let me show you. Remember what this statement is saying. On a circle, we're saying we have an angle B, right? Some angle B, and that sine of it is 0.42, right? 0.42 something. That means that sine of the angle is positive, which means which quadrant could we be in? For sine to be positive, we could be in this quadrant somewhere here, or this quadrant over here somewhere. Now, I don't know what this angle, I don't know what that angle is, right? I'm not saying it's 45 degrees. I'm just drawing it that way. Do you agree? Boy, those are supposed to look like they're the same height. Do you agree that the y-coordinate, the distance here, and the y-coordinate here are the same? So sine of that angle, since sine of the angle is the y-coordinate, it could be one of those two angles, yes? Y'all okay with that? So the first angle over there, when the computer spit back 25 degrees, the reason why the computer spit back the 25 and not the one in the second quadrant is because when we do inverse sine, the computer cuts off the second and the third quadrants, doesn't it? The computer says, you can't have that. That's what the computer said. But in reality, all we know is that sine of B must be 0.428. So it could be both angles, right? We were the ones who came in with the inverse sine to be able to get the angle with our calculator. But in reality, we don't have that restriction. Do you understand the difference? We're using the calculator to get that first reference angle. But just for that, we still have to look at the possibility we could have two answers here. So what could the other angle possibly be? So it could be this, or what? It would be 180 minus, because now we're in degrees, right? So wouldn't this angle here be a half rotation would have been 180 degrees, but then take away the 25.3743. Do you understand that? Questions? Have I told you all about cartwheels? I haven't told you all about cartwheels. I've never been able to do a cartwheel in my life. I've always wanted to do a cartwheel because I can't do a cartwheel. If I could do a cartwheel, I would actually do a cartwheel in this class to try and get y'all to get excited. But I can't do a cartwheel. What's that? You had a chemistry teacher do a cartwheel? Yeah. See? Try and get y'all enthusiastic, pumped up. Maybe I should just do it, just try it and hurt myself up here. No? Does anyone have any questions on how we're going to get this other possibility for B? No? Okay, so do 180 minus that 25.3743, and you get 154. So B could also be approximately 154.6257 degrees. And I'm taking it out more decimal places than you would need to, all right? You could just go like 1 or 2 decimals and I'm okay. All right, so B could be 2 angles, right? Well, hold on. Go back up here. What was A? 40? Could B be 154? No, because then you would have both those angles together would add up to be over 180 just by themselves, right? Which is not allowed. So we will throw this one out because it's too big. But that's not always the case, so you must check them. You must make sure that that's not happening. Understand? Okay, so we only have one possible answer here for B. Once I know B, what else can I get? Since I know what angle A is and I know what angle B is, then I can also find angle C, right? Now, I know that A plus B plus C must be 180. Angle A was 40. Angle B we just got was 25. I'm just going to say 25.37 degrees. And then plus C must be 180. So just do some subtraction there. $114.63. All right, I boxed it. I should have boxed my capital B back here. Questions? Okay, so where am I at? I've got capital B. I've got capital C. I need little c, right? Little c. So to get little c, I'm going to use law of signs again. I'm going to use the one that has c on top and sine c on the bottom. And what am I going to compare it with? What other ratio? Use the A again, because look, the A is fixed. I mean, no one's going to mess that up because it's already given in the problem. So to find little c, I'm going to use this. Little c over sine of c must be little a over sine of a. Little c is what I want. Sine of c is sine of 114.63 degrees equals little a, which is 4, over sine of 40 degrees. Right now we're finding little c. So you go through this, right? You multiply both sides by sine of 114.63. You divide by sine 40. Anybody? 20.24? 24 point? Oh, 4.2. I thought I heard 4.24. Okay. All right. Now, I'd like to write something down. I'd like to just list out A, B, C, and then little a, little b, little c. Okay, it was 40 degrees. B was, what was it, 25.37 114.37. C was 114.63. Is that not right for C? Oh, A was what? Oh, you know what? Was I using the A from the previous problem? Oops. Sorry, everyone. Yeah, go back and fix it. See how I put the 4 there? A was 3. I was thinking of the previous problem. Wasn't A 4 in the previous one? Fix it, because that's going to obviously throw this off. This is 3. This is 3. That's going to change the answer, right? Oh, so you did it right. I just wrote it down wrong. So 4.24. Okay. Everybody agree with that? Anyone disagree? We okay? All right, so look, I wrote these down, A, B, and C. Now over here, let me write down what the sides are. It was what? 3, and then what? 2, and then C was 4.24. Now, this is definitely not a way to check your answer to make sure it's right, but this is something you can do to note if you did something really wrong, you can see it by looking at this. The smallest angle should match the smallest side, and the largest angle should match the largest side, and the middle angle should match the middle side. So you can see that my largest angle, right, is 114, and that side is 4.24, which is the largest side of the triangle. And then the smallest angle is 25.37, and that is the smallest side. And then the middle one is the middle. Got it? Like I said, it's not a check, because I could be off a little bit on my answers, but you know, if this 114.63 came out to be like 1.27, something's wrong. Got it? Something's wrong. Okay, so we're going to end it because I do want to review, but I want us to just think about this for a second. What if you were given this? This is just thinking ahead as an example. What if I told you A was 2, B was 4, and then the angle C was 32 degrees? And I ask you to solve the triangle. Notice anything? I don't have 2 of anything, exactly. I can't set up a ratio. No matter how I do it, I can't do it, right? I mean, using law of sines, what I'm trying to find is capital A, capital B, and little c, right? So what if you try capital A? You do what? Sine A over 2, and then you need all the information from the other one, don't you? You need everything about B or everything about C, which you don't have. Or if I try and find capital B, I'm going to need all the information about A or all the information about C. Do y'all follow what I'm getting with that? If I want to find little c, I'm going to need to know everything about A or everything about B, but I don't. I only have one angle. I can't figure out the other angles. So we're pretty much stuck, right? Law of sines is not going to work here, which is why we have another law. It's called law of cosines. And law of cosines will allow us to handle this. And those are the 2 things that that I'm going to try and get you exposed to first class next time after the Thanksgiving break. All right? So that way, given any triangle, you should be able to solve it. All you need is the law of sines and cosines. Those are the only 2 laws you need. If you have those 2 laws, you can solve any triangle. All right? But we're going to stop here, and we're going to talk about the review. So I know that the review, like I said, that's a copy if you want. The review I put online, I emailed it to you. There was a study group on Friday that I had told you all about. I only had one person show up, but I was there for like 4 hours going over problems. So what I would recommend is, hopefully you've started this, but it took me an hour and a half to do the first 21 problems. So that means probably should take you like 4 hours minimum to do the first 21 problems. I mean minimum on average. And then there's another 7 problems. So this is a review. Your test is definitely not this long, but if you can get comfortable with all these topics, you're going to be good on the test. I'm not going to surprise you with anything that's not on here. All right? So I posted all of the detailed solutions to the first 21 typed out problems. I would like to talk about the other problems on the back. Unless someone has a specific question, I will address that first. Anyone have a specific one they want me to do? Yes? 7, the typed one or the handwritten one? Very good. That was the one I wanted to start with, actually. Okay, so I'm being asked about number 7. I'll write it down. It says, if sine of theta is √3/2 with, you know what? Let me cheat a little bit here. Let me get the exam review. This is the problem right here. If sine of theta is √3/2 with theta between pi/2 and 3pi/2, and cosine beta is equal to -1/2 with beta between 0 and pi, then find the following. So let's take a look at, first of all, seeing if we can determine what these angles are. I mean, can you tell me what these angles are? What's theta, what's beta? From just this given information. Well, I know that I'm in the, second or third quadrants, right? I'm in the second or third quadrants because I'm between pi/2 and 3pi/2. Sine is the y-coordinate, right, of this angle. Where's the y-coordinate √3/2? Positive √3/2. Somewhere up here, right? Do you know that angle? What is it? 2pi/3. That angle is 2pi/3. Why is it not down here in the third quadrant? Because it says that sine is positive, right? Sine is not positive in the third quadrant. So we could scrap that one. That's why we're not looking down there. So I know what theta is. Theta in this problem is 2pi/3. Questions? I'm just jotting this information down. I'm going to come do all these in a second, but I'm figuring out what theta and beta are first. Sure we're okay? All right, what about beta? Let me draw another picture. I'm saying that beta must be between 0 and pi, so I'm not in the third or fourth quadrants. Cosine of beta must be -1/2. Cosine is which coordinate? X-coordinate. Where's the x-coordinate? -1/2 over here. What's that? I can't hear you, I'm sorry. Is it the same angle? Is that what you're saying? Yes. It's the same place. Beta is also 2pi/3. Right? This is basically saying, where is your x-coordinate -1/2 on the unit circle? You have to be in either the first or second quadrant. That happens only in the second quadrant. Now, everything else is just applying the formulas off your sheets. You know what theta is, you know what beta is. So let's do part A. What is sine of theta plus beta? Well, we look at our what are they referred to as? Our sum and difference formulas. Our sum and difference formulas in the bottom left of our formula sheet says that this is sine theta cosine beta plus sine beta cosine theta. Yes, that's what part C is going to be. But on the test, I would not expect these to be the same angles. Yeah, these will be most likely different. Okay, so let's do this. What is sine theta for us? Sine of theta. Well, theta is 2 pi over 3, right? Sine of 2 pi over 3, we already knew what that was, right? Root 3 over 2? Okay, that's root 3 over 2. What's cosine beta? Well, we knew that also, right? It was negative 1/2. Plus, now what's sine beta? Well, sine beta is sine of 2 pi over 3 again. Sine of 2 pi over 3 was root 3 over 2. And cosine theta was cosine of this angle, which was cosine of the other angle too, so it turned out to be negative 1/2 again. So this would be equal to negative root 3 over 4 plus negative root 3 over 4, which would be negative 2 root 3 over 4, which is negative root 3 over 2. So just multiplying these two fractions, multiplying those two fractions, you get these. Since they have the same denominator, you add the numerators up, and then you reduce the fraction. 2 over 4 is the same as 1 over 2. That okay? How about the next one? Cosine theta minus beta. I'm going to go to the formula again. According to the sum and difference formula, if I'm using the subtraction, be careful on this, right? If I'm using subtraction, this will turn into cosine theta, cosine beta, but then what? Plus sine theta, sine beta. What is cosine theta? Negative 1/2? What's cosine beta? Negative 1/2 again? Y'all follow? What's sine of theta? Root 3 over 2. What's sine of beta? Same thing. So multiply these together. Negative 1/2 times negative 1/2 is 1/4. Plus, what's root 3 times root 3? 3. And then 4 on the bottom. What's 1/4 plus 3/4? 4/4, which is 1. Now look, I do realize, everyone, that because theta and beta were the same here in this example, I do realize that this theta minus beta would have been 0 because they're the same angle. And I understand that cosine of 0 is 1, and you could have done that very easily without doing this work. But understand that on the test, the chances of theta and beta being the same angle are about 0. So you need to know what the formula is to be able to do this problem, all right? I know that because I'm going to make the test, right? So it's not going to be the same. C. So for part C, what are we being asked for? Sine 2 theta. So for sine 2 theta, now I'm going to my double angle formulas. My double angle formula says sine 2 theta, 2 sine theta cosine theta. I'm using double angle formula. And that's going to be 2. Now sine theta we already said was root 3 over 2. And then cosine theta we said was negative 1/2. I believe one of those 2's will cancel. So you should just get negative root 3 over 2. That matches the answer from part A, doesn't it? Didn't that match the answer from part A? And that was only because theta and beta were the same. So when you do theta plus beta, it's the same as saying theta plus theta, and theta plus theta is 2 theta. So this answer should match. But again, that's only because they were the same angle. Okay, how about part D? Cosine 2 theta would be, well, you have 3 formulas to choose from, right? 3 of them. So you pick any of them. It doesn't matter which one. I'll just pick 2 cosine squared theta minus 1. I'm just going to pick that one. So this becomes 2. Now what's cosine theta? Negative 1/2. But then squared, then minus 1. So look, cosine theta squared means you take cosine theta first, which is negative 1/2, and then you square it. Then you multiply by 2, then you subtract 1. So square 1/2, you get 1/4. Square negative 1/2, you get 1/4. 2 times 1/4 is 1/2. 1/2 minus 1 is negative 1/2. Part E, sine theta over 2. So you have a formula for that, but it wasn't on your sheet, so I had you write it down on your sheet, right? According to this should be plus or minus the square root of 1 minus cosine theta over 2, right? That's what it should be. And the plus or minus up here, we are going to have to determine which one it is, but I'll do that at the end. So this should be plus or minus square root 1 minus cosine theta is 1/2 all over 2. 1 minus 1/2 is 1/2. What's 1/2 divided by 2? 1/4. And what's the square root of 1/4? Do square root on top and bottom separately. Square root of 1 is 1. Square root of 2 is, square root of 4 is 2. So you get 1/2. Now the question is it positive or negative? So I am interested in knowing what theta over 2 is, right? Like, what is this angle theta over 2? Well, theta, going back up to my picture, theta was in what quadrant? Right here. Well, let me go up to this. Theta was right here, right? Take this inequality and write it down. I said, so I'm going to say, but, did I, let's see, it was sine. Yes, this should be minus, this would be minus minus. Yes. Okay, well, I'm glad you brought it up eventually. I wish I would have said something earlier. That was minus minus. Right? Cosine of theta was negative 1/2. Wasn't it? The formula has a minus in it, but if this is negative, that's going to turn that into a plus. That changes everything. I apologize. What is that going to be? What's 1 plus 1/2? 3/2. What's 3/2 divided by 2? 3/4. So please change that. This right here becomes 3/2. And then when you divide that by 2, you get 3/4. Now when you do square root You get plus or minus the square root of the top over the square root of the bottom, root 3 over 2, not 1/2. Okay, what were the restrictions on theta here? Pi over 2 was less than or equal to theta was less than or equal to 3 pi over 2, right? That was what was given in the problem. But I am interested in knowing what's happening to theta over 2. So if I just take this inequality and I divide everything by 2, divide this by 2, divide that by 2, divide that by 2, I'll have a new inequality, and that'll tell me my restrictions on theta over 2. So this turns into pi over 4 must be less than or equal to theta over 2, must be less than or equal to 3 pi over 4. So what quadrant is that in? Where's pi over 4? Pi over 4 to 3 pi over 4. Isn't that somewhere in this range? Somewhere in here? Somewhere? Right? I've got to be somewhere in here. And I'm interested in knowing what sine of that is. Sine. Well, sine is the y-coordinate, isn't it? So over here, in either the first or second quadrant, your sine is positive, right? So I know that this is actually going to turn into the positive root 3 over 2 because of this. How would you do cosine beta over 2? Pretty much the same thing, right? Do you want me to do that one? I don't mind, or I can give you something else. Yes? Okay. Cosine beta over 2. This is F. Cosine beta over 2 will be plus or minus the square root. This time it's 1 plus cosine beta all over 2. This time, cosine of beta is what? Let me get it right this time. It's negative 1/2. So it's plus negative 1/2 over 2. Now, we already did that one a second ago, right? This one will turn out to be plus or minus 1/2. We okay with that? Now, which one is it, plus or minus? Well, give me the restrictions on beta. What were they? 0 to pi, right? So cut that in half, right? Divide everything by 2. And you get 0 is less than or equal to beta over 2 is less than or equal to pi over 2. So you are in which quadrant? We're in the first quadrant, right? We're somewhere in here. What is cosine in the first quadrant? Positive. So it'll be the positive answer. Make sense? Now, let me give you something a little more realistic for the exam, all right? And we won't go through all the A, B, C, D, E, and F, but let me just show you something that I would be more likely to put on the test. Something like this. If sine of theta equals 3/5, let's make it negative 3/5, and pi is less than theta is less than 2 pi. You know what, let's make that 3 pi over 2. If cosine of beta is see here. What was that one? 1/2 with 3 pi over 2 less than theta less than 2 pi. Find all 6 of those things again. All right? Do all 6 of those things again. So first thing I need to do is figure out if I can figure out what these angles are. Right? In the last problem, it was easy to do because I was able to determine the angle right away, right? Looking at this one, though, this one I can figure out right away what the angle is, right? Because look, we're saying where is the x-coordinate, right? Because cosine beta, where is the x-coordinate 1/2? But you have to be in the 4th quadrant. Where's the x-coordinate 1/2? What angle is that? 5 pi over 3? Everyone agree with that? So I know what beta is, right? I'm in business. Beta is 5 pi over 3. Good. Now, the other one is not as obvious because -3/5 is not one of your common coordinates on your unit circle. So the question becomes, how do we handle this? Well, for this one, what I do is I figure out what quadrant I'm in first. So I'm in which quadrant? 3rd. So I can throw out these. And then what I'm going to do is I'm going to draw a triangle in this quadrant as follows. Now, remembering that when we say sine of theta is -3 over 5, that means that we have the opposite side over the hypotenuse, right? That's what sine means. Then I can label this triangle -3 and 5, where my angle I'm looking at is actually that reference angle, this reference angle. Sine of this reference angle is -3 over 5. Do y'all agree? And then that allows me to draw the rest of the triangle. I can find the x-coordinate, can't I? And so the x-coordinate there, if you do Pythagorean identity, you'll get 4, yes? But it'll actually be -4 because we are in the 3rd quadrant, and so both the x and the y coordinates both have to be negative, yes? Okay. Now, because of that, not only do I know what sine of theta is, don't I also know what cosine theta is? Cosine theta would be what? -4 over 5, adjacent over hypotenuse. And that's all I'm going to need for all of those formulas, right? For all parts A through F, all I really needed to know all those formulas was what sine of theta was and cosine of theta, and sine of beta and cosine beta. And so now you go through the whole thing. So let me just do the first one. I'll do part A. Part A would be what's sine of theta plus beta? Well, that would be sine theta cosine beta plus cosine theta sine beta. What's sine theta? -3/5. What's cosine beta? So now go to beta. Cosine beta was given to me to be 1/2 in the problem, right? So this would be 1/2. Plus, what's cosine theta? -4/5. And then what's sine beta? Well, you just need to figure out what sine of 5 pi over 3 is, which would be -√3 over 2. Everyone follow? Okay, so then you multiply and then put them together and you get your answer. So I would expect something more like that, where I give you some information about sine theta and cosine theta perhaps, or theta and beta. One of them might be right off the unit circle, but I can promise you one of them will also require a drawing of a triangle. Okay, any other requests on this? Yes. Do you have a particular one? Well, what I will say is on the typed ones, I put number 12. I did the answer, okay? I posted them online. I said on number 12 that I won't give you something like number 12. 12 is kind of a beast, but I did put it on here. So let me see. Whoa. Whoa. Uh-oh. Where the heck are all the answers? Oh, there we go. So what do you want to see? It was 12 to 1? Yeah. Did you switch? It worked out pretty good that way? Yeah, see, this is it. This is the way that I did it. And I did it this way because I told most of you that if you ever got stuck to go to sine and cosine. So, look, I mean, you look through this on your own. I don't want to eat up time because I won't give you something like that. Maybe it's like a bonus or something, but that might take too much time during a test. What about the other ones? Well, I mean, anything out of here? I mean, look, the identities, I mean, if you've done them, that's the thing. I'm not going to give you an identity just like, you know, here, do one just like this. I mean, that's the whole idea of an identity is that you just have to figure out a way to get from one side to the other, you know? And the only way you can do that well is if you're comfortable with all the trig stuff. And that's what we're testing. How comfortable are you? If I have to tell you, okay, it's going to be just like this, then you're not comfortable yet. Yes? If it makes some sense, you know, as long as it makes sense what you're doing. Let me give you... With the identities, you know if you're done because it has to look like the other side. Like simplify? The simplify ones? Yeah. Well, yes, definitely you would get partial credit, even if you didn't take it further, that it get more simplified. Like maybe on this one you would have left this as like secant squared. Well, let me see. Left-hand side equals right-hand side. That's what verified means. Yeah. We still have some time. I don't want to not anything. Solving equations. That's right. Every time I ask you to solve an equation for this test, general solution only. I'm not going to ask you for the solutions between 0 and 2 pi. So you don't have to plug k's in, but you need to make sure that that general formula is okay. Nothing off of the solving equations? So do you all feel ready, or are you silent because you've been silent pretty much all semester with me? Wait, how do you feel? I mean, do you feel prepared? Do you feel like this is probably the hardest test, I think, in this class? The identities are always the hardest because you can be pretty good at identities and then all of a sudden you just blank and you cannot get it to work. And then, I mean, it's not really fair that you're tested off of that question, but it's the way it is. Yes? On the handwritten ones? No. Okay. Let me see, is this it? Yeah. All right, yes. So these two terms are separated by subtraction, and so I'm looking for a GCF right away. All right, I don't know why. That's what I wanted to do because this has multiple secants in it. The other one has multiple secants. I see this has secant to the sixth. That's secant to the fourth. So I can pull out a secant to the fourth. Just like if this was x to the sixth power, x to the fourth power, I could pull out x to the fourth, right? So I'm pulling out secant to the fourth. But then I also realized they both have a secant x tangent x, secant x tangent x. So I pull that out also. So this is what I've pulled out. What's left is what's in the black. So when I pulled the secant to the fourth out of this, I was left with the secant squared. When I pulled this out, it's gone. So the only thing left out of that first term is this. Do you agree? And then when I pulled this out of the second term, it was everything there, right? So the only thing left is a minus and then a 1. But you have to have it because you would distribute this blue thing back through, right, to get that top part. And then realizing secant squared x minus 1 is tangent squared x is the Pythagorean identity, rewritten a little bit. But that's a Pythagorean identity to this. And now if you just put these all together, you've got 5 powers of secant, 5 factors of secant, and you have 3 factors of tangent. That make sense? Yes. I'm not saying that's the only way it could be done, but that's the way that I did it. Anyone do that different? Anyone who tried this? No? Any others? Yes? I'm not going to design it that way. I'm designing it off of the types of problems that I want to have on there. So like number 7, the one that y'all asked about, the ones I just did 2 of them. That's a good problem because that has a lot of formulas right there, just application of those formulas and being able to recover the drawings and stuff. I like that problem. I can guarantee you a problem like that. Solving the equations. I mean, all the ones I gave you on solving the equations require some techniques. You know, there's factoring in there, right? College algebra type factoring, 3 terms, AC method type thing. I guess to answer your question is no, I'm not intentionally going to make sure every formula is hit. That'd be a long test. No, y'all are going to let me end class early with 20 minutes left and no one has questions? 17. Yeah, 17 should have caused an issue because that was the last topic we covered. And we didn't really get to cover it as heavily as I wished. Yeah, this is a really messy problem. All right. Look, I can tell you that number, I can tell you for sure that like something like 12, I won't put on there. Like I said, this review is what Christy had on hers, all right? So I normally would not put that problem on the test. Normally would not. But I don't like to tell people, you know, yes, this is going to be like this or not, you know. It's the fact you have a review is a good thing. I mean, you know what I'm saying? As if you move on to Cal 1 and stuff, we start to not give you reviews. Like the whole idea is, can you study yourself, or must I guide you through? You know, do I have to guide you to study, or can you do it on your own? Can you go back, look at your own homework, look at your notes, and study? Does that make sense? Because at some point the reviews go away, and it's just we're going to have a test over what? Over what do I need to study? Everything we've done. That's what you study. So can you organize it all? All right, so let's talk about this. This one, the problem here is that you have 2 terms, and you have it equal to 1/2. So we have a formula that allows us to take a sum or difference and turn it into a product. And I put what the formula is right here. It's on the bottom right-hand corner of your page. It's sine of u minus sine of v is equal to 2 cosine u plus v over 2, sine u plus v over 2. Here, u and v are everything inside there. So here's the formula. This is equal to, the left side turns into 2 cosine u plus v over 2 times sine of u minus v over 2 equals a half. And then when you do this, these pi over 6's cancel. You're left with 2x. 2x over 2 is just x. And we got the 2 out front. This one over here, your x's cancel and your pi over 6 add together. Pi over 6 and pi over 6 is pi over 3. But then you divide by 2, you get pi over 6 again. And then the right side is still 1/2. Are you following up to that point? It's just, I don't know. Because, well, here, when you're solving an equation, no, I mean, I'm being honest. When you're solving an equation, you like to have things that multiply, right? Like that's the whole idea of factoring, right? When you have like a quadratic, you try and factor the left so that you can set each factor equal to 0. Yes? That's kind of the motivating thought, except for the fact that I don't have 0 on the other side. So that's the danger in that. Naturally, I'd want this to be equal to 0 and then factor, right? The fact that it's not 0 is why I said I don't know what would make me want to do that. Because if it were 0, I'd say exactly, because when you have something equal to 0, you would want to factor. But it's 1/2, so you don't want that necessarily. But that's what you wind up doing, and it works. So I guess it would be more like maybe you kind of start to see that's sine of u minus sine of v at some point. And so you say, what can I do with that? Well, I have a formula, make it a product, see what happens. The what? Okay, yeah, I see what you're saying. And that, in fact, is where that could come from if you rewrite things appropriately. So yeah, there's different approaches. So you wrote it as, that first one was like sine u plus v, right? And then you said minus sine u minus v, and then rewrote it, and it probably worked out similar. So this way I did is not necessarily the only way. All right, so once I'm here, sine of pi over 6 is 1/2. And then that 1/2 and that 2 go away. And I'm just left with cosine of x is 1/2, which is unbelievably nice, isn't it? Are you following still? Yes? And so this is just saying, where's my x coordinate 1/2? So I go to my unit circle, it's here and here. So I get my general solutions, and I'm done. Now, if things had not worked out this nicely, then I would be in trouble, but that's the way they worked. Yes? Mm-hmm. Oh, I moved the 1/2 out in front because it's multiplication. And I just did half of 2. Just multiply these two together. Half of 2 is 1, so it's just cosine x. And I didn't touch the other side, just left it alone. What else? This test, I've said this test is a challenge because you have to be comfortable with everything. But I know it's not realistic to be completely comfortable with everything unless you've had the time to actually practice. I think I compared it to, like, has anyone run a marathon? I was asking, no one replied, but it's the same sort of thing. It's like anything else, right? Right? You don't just become an expert on something overnight. You have to get used to it, right? So I know that there are people in here that are working very hard on these identities, trying, and I think if you do put in the effort and the time, it will start to click. It will start to come along. But if you just watch someone do it and you're not practicing it, and every time you see me do it, you go, sure, yeah, got it. Sure, I could do that. No problem. I see that. No issues. This test will be hard because the identity, if you're not doing them, it's not natural to just be able to just spit out the answer. And you have to be prepared to fail and start over. So we'll see. I mean, I think there's enough on the test other than identities that you can still do well on this test and then, trip up on the identities, but Like, the identities are great also because you know you got the answer, right? You're not going to be like, man, I don't know if I got, you're going to be, you box it, you're happy. You know you got it. Yes. Uh-huh. Yes. Okay, so this one I can talk through pretty easily. This is an equation I'm trying to solve. The issue that I saw was that two of my trig factors had x in them. The other trig factor had 2x. And so what I was trying to do was get everything in terms of x. Now, maybe I should write down why I didn't just leave it. What if I had started off and brought everything over to one side of the equation? Maybe I should look at that first. If I would have brought everything over, this is what I would have had, right? The problem with this is, again, we have subtraction. So I'd like to turn this into a product. I try and factor something here. I can't factor it because I don't have a GCF. Like, I don't have a sine x in both that I can pull out. I don't have a cosine x in both that I can pull out. Do you see that? So I'm kind of stuck at this point. But then I realized that sine 2x, I can convert over with the double angle identity, right? Double angle identity turns sine 2x into 2 sine x cosine x, or sine, yeah, it's x in this problem. So it'll turn this into this. And if I do that and I rewrite this, and then I brought everything over here on this line, I brought everything over to one side, then I notice I do have a common factor of cosine. And I can pull that out and then set each of those to 0 and go through and do my little general solutions on each one. Make sense? This one was kind of weird, 19. It doesn't look that intimidating. But it says find sine 2u, cosine 2u, tangent 2u if cosecant u is 3 and u is between pi over 2 and pi. So what does it mean to say cosecant of u is 3? It means the reciprocal of cosecant, which is 1 over sine of u, must be 3. And then multiplying both sides by sine of u and dividing by 3, you get sine of u is equal to 1/3. And your angle u is between pi over 2 and pi. So I know I'm somewhere over here. I know sine is positive, so I'm in the second quadrant. And then see, I drew a triangle, a reference triangle. Because sine tells me I have, what, opposite over hypotenuse? So here's my triangle, my opposite and my hypotenuse. If I have the two sides of the right triangle, I come up with the third by using Pythagorean, right? But why did I use negative root 8? Because I'm in the second quadrant. The x-coordinate, right, of that triangle must be negative. So what that allows me to do is get my two basic trig functions for that angle. Sine of the angle is 1/3, I knew that. And then cosine of the angle would be adjacent over hypotenuse. And so from that, are there any questions on that? From that, I can figure out what sine of 2u is by using double angle formula. Sine of 2u is 2 sine u cosine u. I just figured out what sine u and cosine u were. I get an answer. Cosine 2u, there were 3 formulas I could use. I chose this one, plugged it in, got this. And then tangent 2u is the sine 2u divided by the cosine 2u. And then just figure that out. So this little triangle thing is going to peek its head out somewhere in this test. You're going to have to be able to recover, you know, the rest of the triangle from some given information on the trig function. We're running out of time. All right, well, I mean, I don't have anything else for you. Make sure you come in rested, fed, and confident, relaxed, and calm on Wednesday if you're taking Wednesday. Who's not going to be here Wednesday? Okay, y'all have a good Thanksgiving. Have a good day, everyone. Yep. Oh, can I stop recording? Okay.